We've all sorted stuff before. Let's suppose I gave you a warehouse full of 1 million cats, and I said, would you please sort all those by age? You might initially wonder where I got a warehouse with 1 million cats, but aside from that question, you're probably going to want to consult a couple of experts. You're going to want to know, okay, how do I find the age of a cat? And the other thing you're going to want to know is, how do I sort these cats so they're not just running all over the place? So you kind of need two separate experts here. One of them is going to tell you how to compare the cats. The other one is going to tell you how to sort them. Usually when we talk about sorting, the sorting algorithm gets all the love. But for comparison-based sorts, the comparison algorithm is equally important. So let's first drill in on that, and then we'll look at some sorting algorithms in a different lecture. I actually don't know how to tell the age of a cat, so I'm going to look at a more boring example, which is playing cards. Playing cards have a suit and a rank, and we could represent playing cards in a kind of intuitive way using strings. So here's the 2 of clubs, the 3 of clubs, 2 of diamonds, the 4 of hearts, the 6 of spades. We can represent the 52 cards in a standard American playing deck using an array of these kind of strings. And in fact, I get a lot of stuff built into Java that I can use. For example, I can actually shuffle. There are shuffling algorithms that'll shuffle that. And you can see here that when I shuffle, I'll get some randomization of the data. If I run this more than once, I'll get a different shuffling. So it's going to shuffle it differently every time. Here, the 3 of hearts is at the beginning. Here, the 2 of diamonds is at the beginning. And that's great. I have a shuffling algorithm. I can also sort. So here I'll use some sorting algorithm. It doesn't really matter to us which one. And then I'll just sort it. So you can see the sorted outcome is always the same. And that's good because I am trying to sort them, so there should be some order, a predictable order. You can see that the order I'm getting here is not exactly what I might have wanted for cards. I'm getting 10 before 2, and going up to the aces, the jacks, the kings, and the queens. Where is this order coming from? If you look at it for a while, you'll see that this is actually alphabetical order on strings. So when we compare two strings, we first compare the first character of the string. 1 is less than 2, and 2 is less than A. This is just because the numbers happen to come before the letters in the encoding of characters that the computer uses. And so that's why we get this order. It's not what I wanted. I would like this to be more meaningful. I would like to have cards that have like order based on suit or rank or something like that. We can code that up. The way we do it is providing our own comparison operator. It's called a comparator in Java. And when you create a comparator, you have to say what you're comparing. In this case, I want to compare two strings. The result I'm going to get is always a number. And the number is either going to be negative, 0, or positive based on the outcome of the comparison. So 0 is used here for equality, negative 1, positive 1 for inequalities. In general, actually, any negative or positive number is possible. So here's an encoding of this card comparator, which finds the suit in these cards. So the suit is just going to be the character corresponding to the suit. So that'll be either C, D, H, or S. And then I'll look at the rank. And the rank is a number. The rank here I can, for single digits, I can find just that one digit. There's only one number that starts with 1. Note that I don't actually have a card for 1. That's called the ace, so it's different. So when I have 1, I can just think it's 10. Jacks are 11, queens are 12, kings 13, aces 14. And when I do this, I'll have an ace high rank. I can then compare these things based on whatever order I like. This is a suit major comparison. So if two things have different suits, I'll compare that first. So if the suit of the first card is less than the suit of the second card, then I will go ahead and say that they're not the same and which order they should go in. If the suits are equal, then neither line 32 nor 33 will cause this to return, and therefore we'll do a comparison based on rank. And then only if all of that fails to return, we know that the cards are equal and we can return 0. So if we run this, we get a better outcome. You can see we can actually sort our cards here based on various techniques. So we have the sorting based on string sort. That's not what I wanted, but when I do the suit major sorting, I get it, organized by suit and then by rank, which that looks nice. We can also swap this around. So if you like rank major sorting, that's fine. You can just sort it by rank. And now you'll get the numbers 2s before the 3s, before the 4s, etc. You might wonder if the suits are in the right order. Turns out, convenient for us, we actually get the right order for poker in the US. So clubs below diamonds, below hearts, below spades. So it actually turns out. You can really see here the three aspects of the problem. So one is that I have a comparison algorithm. There's two possible comparison algorithms here. One is the card comparator that I've created, or the built-in comparison that comes along with string. Then I actually have the particular set of strings that I've chosen. These 52 strings are not in any way special to the string class. They're just strings, but I've chosen that data because it's interesting to me, just like the million cats in that warehouse are interesting. And then finally, we have the sorting algorithm, which I haven't talked about yet. And that sorting algorithm you can see here is parameterized by a comparator. So there's two ways to invoke my sorting algorithm. I can invoke it without providing a comparator. In that case, it will use the natural order. That's the order that comes along with strings themselves. And if I provide an auxiliary comparator, then the sorting algorithm will use that. So it'll sort the strings based on whatever I've told it to do. The terminology that's used for these two different kinds of comparison algorithm is the internal or the natural order, and then an external order. So the natural order is provided by whoever defines a class. So Java defines the string class, and they've decided to order strings by dictionary order. And that makes sense for strings. The way this is specified is that the string class implements the comparable interface. That interface has one method called compareTo. So this takes an argument, that, and compares it to this. This is a member of the string class comparing itself to something else. And we'll get a negative number if this is less than that, a positive number if this is greater than that, and 0 if this and that are equal. We can provide an external order by realizing the comparator interface, like card comparator in my example. So here's the interface for comparator. And note that comparator is coming from outside. So this is not part of the string class itself. So I'm not comparing this. I'm instead comparing two external things. I'm comparing some object 1 and object 2. And if object 1 is less than object 2, we return a negative number. If object 1 is greater than object 2, we return a positive number. And if they're equal, we return 0. And that's precisely what's happening here. Let me just restore my original comparison operator, and we can see what happens with that. I've added on a little bit of code at the end here to show some deficiency of this particular encoding of cards. So it's great. I've got strings, they represent cards, but if you have this deck of cards, D here, that I give to someone, if this is not my own deck of cards, or even if I am using this deck of cards in a sort of complex program that I've written myself, I might actually end up getting the deck of cards over someplace where it could have something bad happen to it. So here what I've done is thrown some random string into the deck of cards, and I just shoved this string ampersand E, which makes no sense in this particular context, into my deck at position 0. So I can still sort this thing, and it sorts just fine, but I've got this bogus element sitting in here that makes no sense from the point of view of a card. So probably my software is going to get broken at some point. How do you write your code in such a way that these kind of accidental modifications can happen? Well, the full solution to this is beyond the scope of this course. We can't do all of computer science in 10 weeks. You'll learn this stuff instead in Software Engineering 350 or 450. That is the course where we talk about how to structure large object-oriented programs so that you don't have this kind of problem where you're stepping on your own code. So consider this just a preview of that course. What I'll do is create a card class, and the card class is going to have a natural order. That means I'll be able to compare cards to other cards. I'll have two data elements, a rank and a suit, and each of these is an enumerated type. There's 13 possible ranks and 4 possible suits, and I can represent them symbolically here. When you create a card, you provide a rank and a suit, and you can print them out, and you can also compare the cards. So how do I compare cards? Well, I look at this suit and compare it to that suit. And note here I'm using the compare to method of the enumerator. The enumerated types are simply ordered in the order that you list them. So if I have a clubs, it will be less than diamonds, less than hearts, less than spades. And likewise, 2 is less than 3, less than 9, less than jack, less than king, less than ace. And so I can do this where I simply compare things. And if I find a difference, I return early. Otherwise, if I don't find any difference, that means that they're equal. It's normal when we provide a compare method to also provide an equals method, because if 2 cards are found equal with respect to the comparison method, we also expect them to be equal with respect to equality. I'm not going to talk about how to properly write an equals method. You'll learn that next quarter when you talk about hash tables. For implementing a hash table, you need an equals method and also a hash code method. And coding up equals is actually a little bit tricky. This is a way that works. It's not as efficient as it might be, because here I'm using the compare to method to actually compare this and that. If they are equal, then I can just return the Boolean comparison to 0 here. So if compare to returns 0, then it's true, they're the same. You'll notice that there's a little bit of an impedance mismatch between the equals method and the compare to method. Note that the argument of equals is object, whereas the argument of compare to is actually a card. And this is something of an engineering choice. It's possible to define equality on any kind of object type. At the very least, you can just say, well, 2 objects are equal if they are the same object. And that's what the default definition of equality does. Instead, if you want to be a little bit more detailed about it, you can say, well, 2 arrays, for example, are going to be equal if they have the same length and they have equal contents. So that's a more nuanced or abstract notion of equality. The real concrete one is just 2 objects. If they're the same object, then that defines equality. They bolted this into the language really early on. They also bolted hash codes into the language really early on, and you'll get that next quarter. But the long and short of it is just that equals is defined for every object in the language, and it's necessary that you also be able to compare for equality with any object in the language. That's not true for comparisons based on inequalities. So those kind of comparisons, really, it's hard to say that you can just pick a way to compare 2 objects. Like, suppose I'm comparing cats and filing cabinets. Is the cat greater than the filing cabinet or smaller? I can tell whether they're equal or not. They're not equal, but how am I supposed to compare them? It's not clear. So comparison is more optional than equality. And therefore, the compare method is a little bit more refined in terms of what you can expect about the object that you're comparing to. You don't have to compare to every possible object. You don't have to tell me how to compare the cat in the filing cabinet. You just have to tell me how to compare cats to cats, cards to cards, filing cabinets to filing cabinets. If you want to see a fully fleshed out example of this kind of card class, look in the algs12 folder in Xcard, and you'll see I've dotted some I's and crossed some T's here. In addition to having my compare to operator and my equals operator, I've also got a proto deck. So this is a deck of cards that I can use as a prototype for generating decks of cards in the future. I actually don't need ever more than 52 objects representing cards in my system because the cards are going to be immutable and I only ever need 52 of them. So when somebody wants a deck of cards, what we'll do is just copy the proto deck and give it to them. So you can sort of see this in an example here where I am going in my main program to get a deck of cards, and that'll just be an array of cards. I can then initialize it and shuffle it and then sort it, and you'll see the output coming like this. Of course, it's entirely possible that the client here doesn't like my card sorting. They may say, oh man, this guy, he's always doing suit major sorting. I hate suit major. I want rank major sorting. And so you can fix that, of course, just by providing your own comparator. So here's a rank first comparator, which will actually do it the way you want. If you're only going to use this comparator once, you don't actually need to give it a name like I've done here. You could use an anonymous inner class, or in recent versions of Java, you can use the lambda notation. And so this would be a shorter way of writing the same thing. I am saying to the insertion sort algorithm, please, for this sort, would you take this comparator? And here I'm specifying the comparator to compare rank first. And so you can see this runs just the same as it would if I had named that class.